In a symbolic agent architecture, the key ideas are that an agent has an explicitly represented symbolic model of its environment, and that decision making about what to do is done via manipulating that symbolic representation. Now, in the purest expression of this whole tradition of symbolic reasoning architectures, the idea is that the internal representation that an agent has of its environment is captured using logic, and the decision making about what to do is done using logical reasoning. So that's the idea that we're going to explore in this particular video and see how, in principle at least, the idea might work. Just a caveat before we start, I'm not suggesting that what you're about to see is an appropriate way to go about building agents. It's a rather naive way to go about building agents. But the point is that it illustrates this principle of representing an environment using logic and making a decision about what action to perform via logical reasoning. So the key idea, what I want you to take away, is that in this whole approach, is that when an agent makes a decision about what to do, it proves a theorem to the effect that a particular action is the optimal action to perform. That's how it makes its decision. It proves a theorem, or tries to prove a theorem, to the effect that a particular action is the optimal action to perform. So in what follows, I'm going to use a bit of logical notation, so it helps if you understand the logic notation, but I hope you'll get the main ideas even if you don't understand the detail. So when in this deductive reasoning approach, when we write a program for an agent, the main thing that we're going to write is a logical theory. A logical theory which encodes the optimal action to perform in any given situation. And we're going to use this Greek letter rho, which looks a bit like a P, to stand for this theory. So this is our logical theory of the optimal action to perform. And as we'll see in later videos, actually this logical theory is usually a set of rules. We very often actually encode that theory as a set of logical rules. Okay, so the program that our agent has is this logical theory rho of the optimal action to perform in any given situation. Well, any given situation is captured by our agent's beliefs, and we're going to use this Greek letter big delta, the big delta here with delta standing for database. So delta here is a logical database which has the agent's beliefs, all the information that the agent has about its environment. So delta here is going to be the agent's internal state. So that's the explicitly represented symbolic data structure capturing the information that the agent has about its environments. So we've got a logical theory of the optimal action to perform. That is going to play the part of a program. And then at any given moment, our agent is going to have a delta, which is a set of logical formulae characterizing the state of the environment. Then AC is our set of actions, whatever those actions are, that our agent can perform. And then we're going to use this logical notation to mean that this phi can be proved from this database delta using this logical theory or using these rules rho. So this can be proved from this using these rules rho. So this symbol here, which is often called the syntactic turnstile symbol, just means that you can prove this from this using these rules or using this theory rho. Okay, so at the moment it's a little bit abstract. Let's see the actual decision-making loop that we're suggesting here. So roughly speaking, what we do is we consider each possible action in turn. So we consider each possible action in the overall set of actions. And we try to prove this predicate do alpha. And the idea is, if we can do that proof, if we can prove do alpha from our current beliefs using our theory of the optimal action, then alpha is the optimal action to perform. So for each possible action, we try to prove that that action is the optimal action to perform. And if it is, then we just say, right, we found the right action to perform, let's just do it. So we return that action. So we consider each action in turn and try and prove that that is the optimal action to perform. So you remember your theory of the optimal action to perform is encoded within that row. So when we write our agent program, so to speak, what we do is we encode that theory. Okay, So suppose we get to the end of this loop and we haven't found any optimal action to perform. Okay? So what we then do is we consider each action in turn and we say, well, is it explicitly forbidden? Right? Can we prove not do alpha? So if we can prove not do alpha, okay, then that means we should not perform this action. But if for some particular action we fail to prove that it's forbidden, then this is a reasonable candidate. It's not inconsistent with our theory of optimal action. So that's the candidate for the action to perform. So the first loop just looks at each action and says, can I prove that this is the optimal action to perform? And if we can do this, if we can prove this predicate do alpha, the idea is that then alpha is the optimal action to perform. If we get to the end of this loop and we still haven't done anything, then we just don't have any good candidates for what to do, so we just return null, so we haven't found a particular action. Let's make this concrete with an example. So this is a 3x3 grid world, and the idea is that we've got a robot which is currently in this middle square here, and there is dirt in this grid world. And the grid world has locations. So this is location 0, 2, this is location 1, 2, this is location 2, 2, this is location 0, 0. And the idea is we want the agent to move around and clear up this dirt. So how might we build such an agent? Well, the first thing is, what does the internal model look like? Well, there are a number of choices that we could make, but we're going to use this particular representation. We're going to use predicates in xy to mean that the location of the agent is currently xy. It currently believes it's at location xy. Dirt xy means there is currently dirt at location xy, and facing D, where D is north, south, east or west, means that the agent is currently facing direction D. The possible actions AC that our agent has are turn, move forward and suck, which is to say switch the vacuum cleaner on. So the idea is that this turn action will turn the agent 90 degrees to the right. Okay? Exactly 90 degrees to the right. And move forward will just move it exactly one grid step forward. So then it's quite easy to come up with a bunch of rules. And here is one candidate set of rules. I emphasise these are not in any sense elegant, and you can easily do better with a little effort, but they illustrate the point. So we've got rules here. This is our row. This is our theory of the optimal action to perform. So for example, the first rule says, if you believe you're in location 0, 0, and you believe you're facing north, and you don't believe there's dirt at that location, then move forward. If you're in location 0, 1, and you're facing north and there's no dirt there, then move forward, and so on. So for example, you can imagine a rule which says, if you're in location 0, 0, and there's dirt there, then do suck. Switch the vacuum cleaner on to clean up the dirt. And it's quite straightforward to expand those rules out into a set of rules which will get the agent to move through this environment, clearing up dirt when it sees it. And the internal representation that an agent has is just made up of a bunch of predicates that look like this, which tell it where it is, what direction it's facing, and whether or not it sees any dirt in the current location. And then on the right-hand side of these rules, we have the optimal actions to perform. So I emphasise, this set of rules, firstly, is a rather clunky and not very elegant set of rules, and you could easily do better. It's not supposed to be a way of actually implementing a vacuum cleaner agent. It's just supposed to illustrate the idea of deciding what to do via logical reasoning. So, in its purest expression, this deductive reasoning paradigm says that the internal symbolic data structure that an agent has is made up of logical formulas which describe the environment. And here, these logical formulas are things like in 0, 0, facing north, and so on. And the second thing that this approach says is that you decide what to do by proving a theorem. And you try to prove a theorem to the effect that a particular action to perform is the optimal action to perform, given your beliefs. So in our examples, we considered in this control loop, we considered each possible action in turn and tried to prove do alpha. And if we could do this proof, then the idea was that alpha was the optimal action to perform, assuming that the world looks like this according to your theory of optimal action.